R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE and BIT SAT. He has more than 16 years experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UG's lecture series in BSc Honours in Physics. In this lecture, we are going to see the superposition of oscillations. This is the session outline for today's lecture. The superposition of oscillations with definition, some examples and the classification of superposition, methods of analysis of superposition and prerequisites to understand the concept of superposition and again the types of superposition. Let us start with the definition of superposition. What does it mean? In the last lecture, we have partly seen the definition for superposition. It is nothing but the addition of two simple harmonic motions. If it is going to be the simple harmonic motion, then the addition of simple harmonic motions, or if it is any oscillation, then it is called the superposition of oscillations. In our curriculum, we have the superposition of SHMs, two or more SHMs. So, this itself is the definition for the superposition. The term superposition is invariably used for combining or composing two or more components in it. In the case of electrostatics, the forces are added due to several charges, then it is called superposition principle. It is like finding the resultant, and in the same sense here also we are going to find the resultant oscillation of several oscillations in the case of superposition. So, it is the summation of two or more oscillations happening at a particular point. Nevertheless, let us see what is the definition in particular has to say for us. Superposition of SHM refers to adding of two or more SHMs together to find the resultant motion. The net displacement of the body in space or time is simply the vector sum of the two individual displacements. In general, we come across the several SHMs combining together at a particular point. We have several practical cases in which a particular particle oscillates not only due to one restoring force, but due to several restoring forces. We know in the case of SHM, the displacement is the restoring force is directly proportional to the displacement, or the acceleration is directly proportional to the displacement with a negative sign, because the acceleration and the displacement are opposite to each other in direction, or the force restoring force and the displacement are opposite in direction. So, in this case, how the particle will behave if more than one restoring force acts on it. So, let us see how the restoring forces combine together to give a net resultant oscillation on the particle. A SHM is produced when a restoring force proportional to displacement acts on a particle. If the particle is acted upon by two or more such restoring forces, each of which can produce a SHM, then the resultant motion of the particle is the combination of these SHMs. So, from the concept of oscillation, now we have narrowed down our discussion to the simple harmonic motion or SHMs only. As I stated, the force, restoring force, is proportional to displacement with a change with the opposing direction, or there is a minus sign in the expression. These concepts we have learnt in the beginning of the concept of oscillations. Now, we are going to see the net effect of several such restoring forces acting at a point. Do we have practical example for this? Very much yes. In many cases, we connect a body with just not one spring, but sometimes with several springs. Each spring is capable of producing a restoring force on the body to which it is connected. If there is only one spring connected, then the body will execute simple harmonic motion due to that one restoring force. If more than one spring is there in the system, then each spring is capable of producing a restoring force, which is again proportional to the displacement with a opposing direction. In that case, how the body will react, how the body will behave? Each spring would produce a force which is having an effect on the body. So, the body will have a resultant oscillation, and in this lecture we are going to see how we are going to analyze especially this kind of superposition of SHMs. This is a diagram depicting how two springs could be connected to a mass m. In the upper case, this diagram, the two springs are connected in series and it is connected to the mass. Each spring is capable of producing a restoring force on the mass to which the springs are connected. Look at this first diagram. The two springs are connected in series and it is connected to the mass m. Each has a spring constant K1 and K2 respectively. So, obviously on this mass the two springs will definitely exert their individual restoring forces. So, this is a good example for how a body will behave when two restoring forces are acting on it. In the same way, the next diagram, if we have a look at it, the two springs are connected in parallel. Here the case is slightly different, but in this case also the two springs will definitely produce a restoring force on the mass m. So, this is also an example for how the superposition principle is useful in practical cases. Just for the sake of example, we have taken only two springs. Like that, we can have several springs connected either in series or in parallel or in series and parallel too, some complex connections. All these are possible in practical sense. So, in these kind of situations, we have to analyze the resultant of these forces acting on the single mass. Here the body mass m we have taken. On other hand, we can consider a point on which these forces act and we can find the resultant effect on the point also. One single spring we have done the calculation, we have done the analysis, but here several springs are connected. This has been taken as an example for the superposition of SHM. Now, when we take the superposition, it could happen in several ways, because in the SHM equation we have several terms like amplitude and then phase, the time, frequency, all these factors, and also the SHMs can join along the same line or perpendicular to each other. So, based on all this we can take up several classifications. Let us see what are the different classifications we have to analyze the superposition of SHMs. Based on direction we can analyze, we can classify the superposition. First one under the category of based on direction, it is collinear direction and the other one is perpendicular direction. Let us see what they are. In the case of collinear direction, when the combination happens, then the resultant will also be in the same line. What is the meaning of collinear? It means the same line, single line. The oscillation could be happening in the same line individually. The resultant is also expected to happen in the same line. Say for example, if we have oscillation along the y direction and another oscillation is also happening along the y direction, they combine together in the same y direction to produce a resultant oscillation. So, in this case the oscillation is said to be the combination in collinear direction. Similarly, we can have it in the x direction also, along x axis, another along x axis, two can combine together, the resultant could be in the x axis. So, these are the examples for the combination happening in collinear direction. Now, we have the second category based on direction is the perpendicular direction. In this case, the two oscillations would happen perpendicular to each other. Take for example, one oscillation would be happening along x axis and the other oscillation would be happening along the y axis. When they combine together, the resultant would happen in a particular plane along xy plane. So, this is also a case of superposition. So, this also we need to handle. In the coming sessions, one by one we will take up for discussion and in detail we will analyze all of them. Now, these are the two cases based on the direction, collinear direction and perpendicular direction. Now, what are the other classifications we have? Let us see. Now, based on the characteristics of the oscillation like frequency, amplitude and phase, these are the characteristics of the oscillation. Based on them also we can classify the superposition of oscillations, like the oscillations which have the same frequency, different amplitude, or same amplitude and different frequency, or phase. So, all these combinations or some cases in which the phases would differ by a particular value or frequencies would differ by a particular value. So, series of such individual forces, the restoring forces or oscillations, those have to be handled. So, mathematically we can deal them. So, this is how we classify the superposition. One is based on the direction, the other one is based on the characteristics. Under each category we have several subdivisions also. Let us see how the direction part is visualized. See, this is one pictorial representation to show how the collinear direction and perpendicular direction would look like. See, in this case of collinear, the oscillation is happening here along the y axis, the x axis is the time axis. So, this oscillation, say for example, the dotted line is one oscillation, the another dotted line with a gray color is another oscillation, and they are combining together to give this solid line as the resultant, and of course they slightly differ in the phase when they combine. So, all these are possible in the case of collinear. And what about the perpendicular direction? In the perpendicular direction, take for example, the green oscillation is happening along the x axis and the blue oscillation is happening along the y axis. Of course, this z is the time axis. So, the resultant would be in one particular plane, xy plane, and here there is no phase difference in this particular diagram, but we can introduce a phase difference also in the case of perpendicular combination. So, there are lots of ways by which the SHMs could combine to produce a resultant motion at a particular point or on a body which is acted upon by several restoring forces. Now, we need to adapt a method to analyze all these categories of combinations or superpositions. What are those categories we have? Let us see. The types of analysis and the prerequisites for the understanding of superposition. To find the resultant of superposition, there are two different approaches, namely analytical approach, which is purely a mathematical approach, and the second one is a graphical approach. In the case of graphical approach, we call that as a phasor method. For the analytical approach, we need to have the prerequisite of the knowledge of trigonometry. The former requires, that is, the analytical approach requires the knowledge of trigonometry, and in the case of graphical approach, the phasor, the later, that is the second one, requires the knowledge of vectors. So, these are the methods by which the superposition of SHMs is analyzed. One is the mathematical method and the other one is the diagrammatic or graphical method. Each method has a prerequisite. The mathematical method requires trigonometry knowledge, and in the case of the graphical method, the knowledge of vector analysis is required. How these could be handled? Let us see some general example of handling the two methods of analysis, so that we could take up the concepts in particular in the forthcoming sessions. But before that, a basic idea we could need to develop our understanding of the superposition further. Let us see how the methods work. Let us now recall the typical equation of SHM. It may appear elementary, but this is very much necessary for the further analysis. Here we have taken the equation which varies, or the point which has displacement in the direction of x. So, that is why the equation has x on the left hand side, which is equal to a sin omega t plus phi. What are these terms? X is the displacement at a particular time t, the x and t are there in the equation. A is the amplitude, the maximum displacement, and omega is the angular frequency, which has the relation with respect to the angular speed of the uniform circular motion, which could also produce the SHM along a particular line of projection, and phi is the phase of the oscillation, which is the initial angular position of the oscillation. So, let us have this base now to have an understanding of the mathematical method of analyzing the superposition of SHMs. This equation is representing only one SHM, the one which we have seen right now. Similarly, we need to have the other equations and then we have to add them all literally. That is called the analytical method. Let us see what it is. There is an example, general example given, the analytical approach. In this approach, the two SHMs are simply added. Mathematically they are added, that is it. Let the two SHMs be taken like this. X1 is one SHM which has an amplitude A1 and which has angular frequency omega 1 and the phase phi 1. The second SHM is also represented here, which has the displacement x2 with amplitude A2 and angular frequency omega 2 and phase phi 2. Now, to find the resultant of the two SHMs, the combination, we are simply add x is equal to x1 plus x2. It is just substituted in the place of x1 and x2, we have the substitution done here. Now, have a look at this equation. When we have a look at this equation, it is to be mathematically handled. See, the two terms, the a1 sin omega t plus phi 1 and a2 sin omega 2 t plus phi 2, these two terms are trigonometric functions. So, only when we have the prior knowledge of the trigonometric identities, we will be able to proceed further in simplifying them. So, that is why the prerequisite is the trigonometric concepts or the identities. Identities are the standard equations. And what about the second method? So, the first method requires the trigonometric knowledge. The second method, how it is done? It is the graphical method. Let us see how it looks like. See, this is the graphical approach. Just for an example, here representation is given of this single SHM. So, let us see how it is done. X is equal to a sin omega t plus phi. The x is taken here along this vertical line. Do not get confused that it is the y direction, it is a vertical line, that is it. So, this could also be the displacement, and we have the amplitude represented here as a, because a is the amplitude, and omega is the angular frequency with which this a could rotate. So, that is why it is shown in this direction, and we have the phase phi represented here as an angle, the initial phase. So, what is the displacement? Its projection along the x. So, this x will be varying as this vector a rotates with the angular frequency omega or angular speed omega. Now, this is only one representation. Like that, we need to represent two SHMs. See here, the first term is shown here, the first oscillation is represented as I have explained for the single case, and this is for the case of second oscillation. Let us have a close look at them. The first oscillation with a1 and phi 1, second oscillation with a2 and phi 2 are shown here. Just for the simplicity sake, we have assumed the two have the angular frequency just omega, they rotate with the same angular frequency omega. Now, what about the combination of these two, how to graphically combine them? It is shown in this picture. See, we have this a1 as it is shown in the first oscillation. The second oscillation has to be just in this arrangement, it is to be done in this arrangement. It should start from the head of this vector, the tail of the second vector should coincide with the head of the first, and it is arranged. The phi 2 has to be again measured with respect to the horizontal. Now, what about the resultant? The resultant is the line joining the tail of the first and head of the last. So, this could be the resultant, which is not shown in this, but the arrangement is explained here. So, this is how the graphical analysis is done. Initially, it may appear little difficult to understand how the graphical method is done, but when we go for several combinations or several oscillations to be combined, then this graphical representation will be very handy and it will be very easy for us to analyze the method, analyze the superposition. So, in some cases the mathematical analysis will be useful, in some other cases the graphical method will be useful. So, we have to judiciously use these methods for the analysis of superposition of SHMs. Let us see how we could further discuss on the concept of superposition. So, in this lecture we have just seen the general view of superposition. The special cases will be taken up one by one in the upcoming sessions, and this is called the type of superposition. Based on the classification, we can approach the superposition in two different types, that is the SHMs with equal frequencies. It is very easy to understand now. See, the frequencies are same, omega is the same here, only they differ in the amplitude, of course in the phi also. And similarly SHMs with different frequencies. See, here the frequency is omega 1, here the frequency is omega 2. So, these two terms are combined together. So, this is also called the type of superposition. We can have the variation in the frequency, or we can have the same frequency also, or they call it as same frequency and different frequency of combination, that results in superposition of oscillations. So, we have got plenty of combinations to discuss about the superposition of SHMs, but we have some selected types only given in our syllabus, like SHMs with same frequency and different amplitude, that is one type, and also the SHMs with different frequencies, maybe with same amplitude or different amplitude. So, like that we will take up some special cases for us to discuss in the upcoming lectures. So, let us see what we have seen in this lecture as far as the superposition principles are concerned. In this session we have seen the concepts of superposition of SHMs. We have seen the definition of superposition in several forms, and we have seen some of the examples, and then the classification of SHM based on the direction and based on the characteristics, and then the methods of analysis, mathematical method and graphical method, and what are the prerequisites, the requirements for the two types of analysis, and also the types of superposition like same frequency and different frequency, etc. Before we wind up this session, let us test our understanding by asking these questions. Define superposition of oscillations. Give some practical examples for the superposition of oscillations. How the superposition of SHMs classified? What are the methods adapted for the analysis of superposition? Mention the types of superposition. We will take up the special cases as I have mentioned, SHMs with same frequency, different amplitude and phase, and different frequencies with different amplitudes and phase, all these one by one in the upcoming lectures. So, we have lot more in store for us. Thank you for listening to this lecture.